put that line, BCrypt engine default cost is equal to whatever number you want, and you restart your server, and your passwords will be getting encrypted with that cost. And a way to verify this is by checking, again, your database, what's between the second and third dollar signs. So you can increase your cost factor, but keep in mind that it does take time to run the hashing algorithm, and BCrypt, when you use BCrypt, it does run when your user signs up and every time they log in. So you can't put like, I don't know, let's say 100 rounds, because it would take your server like a ridiculous amount of time to run through that hash algorithm. So with my laptop personally, I have a i5 third generation, and anything more than like 13 or 14 starts getting really, really slow. So keep that in mind when you're increasing your cost factor. You don't want to be putting anything like 100 or something in there. For you guys that are familiar with Big O, it's the runtime increases on the order of 2 to the n being your cost factor. But that's it for my presentation. I hope you guys learned something. If you guys want to learn more about the sign-up system and the login system that I use, it's all in railstutorial.org/book. It's a free book by Michael Hartle. He also covers advanced login in chapter 9, if you guys are interested in that. He doesn't cover the cost, I think, but you can just Google that really. But yeah, that's it for me. I hope you guys enjoyed. Happy New Year.
Thank you so much, Ibteda. Are there any questions from the audience for our speaker? Okay, we're gonna have to pass this along. Catch, hold on.
It's weird speaking into a cube. Two quick questions. One, could you kind of more clarify why it was, you said that you shouldn't implement the 2A, at least at that stage, in Rails as opposed to PHP and such? Because wouldn't 2A be a good idea in general, since a lot of times the way passwords get broken is due to user error?
Yeah, sure. So 2A is, so the way BCrypt was implemented was that certain implementations had different algorithms, right? So there were bugs in PHP and OpenBSD that required them to revise from 2A, but Rails did not have, or Ruby rather, does not have that bug. So really it's just not necessary to even like worry about that, because it's not a problem for us. It was never a problem for us in the first place. It was a problem for the cryptographers.
Okay, I guess John's up with that. And two real quick is, do you think that your methodology of implementing in Rails would work against hashing programs such as like Jack the Ripper? I mean, John the Ripper, sorry.
Sorry, I'm not familiar with that. But I mean, it would be able to get cracked. I mean, it's just making it stronger. It's just a matter of time, really. Like everything gets cracked eventually. Okay. It's just a different way of doing it.
Okay,
well, I'm not sure what you're talking about, but I know that BCrypt is not a foolproof solution.
Okay, just one clarification. Thank you.
Sure thing. Ibteda, do you by chance know if BCrypt includes salting when?
Yes, it does actually.
Any other questions from the audience? All right, cool. Thank you so much. Thanks again. Cool. Okay, while we're setting up here, just you all between each other, if you are hiring or if you're looking for a job, try to mingle. Raise your hands if you're hiring, if you're here and you're hiring someone for your company. Hire so we can see them. Okay, cool. Those of you who are looking for a job, talk to those folks. Hopefully match up. And let's get you set on Zoom.
I thought you wanted you got the second one. Hand me this one off to you.
All right. Up next, we have Sun Lee, who will talk to us about making Ruby code faster with multithreading. Brief show of hands who here had used multithreading in production environments. Who here knows about multithreading? All right, cool. I think this is going to be a great audience for this. Thank you so much, Sun Lee. Take us away.
Yeah, you actually asked my first question. That's good. So, right, one more time. Who here is not familiar with multithreading? I just want to get another raise. All right, cool. Yeah, for everyone who did raise their hand about using it in production, you can just start zoning out now because I'm going to be talking about stuff you already know. But hopefully you'll learn something. But yeah, nothing too crazy new. But yeah, just a little bit about me. My name's Sun Lee Beatteay. I'm a software engineer at DigitalOcean. My shirt as well. I'm also a technical writer, so I write some blogs at Medium. So if you want to read those, you can follow me at SunnyB. And then if you want to see my GitHub or Twitter stuff, I don't go on Twitter much, but I'm not going to stop you from following me. But those are my socials there as well. So yeah, so the main key takeaways that I want you to get out of this talk are going to be what are processes, what are threads, and how they work. Also, concurrency and parallelism, you might hear them used interchanged, but there are subtle differences between them. They're not exactly the same thing. So I'm going to talk about those differences. And lastly, I'll be talking about actually how to use multithreading to speed recode. So I'll be going over race conditions, what are those, and how to prevent race conditions using mutexes. And so actually partway through this, I'm going to do some live coding. So I'm going to put the microphone down. So hopefully I'll have to speak louder, you can hear me. All right, so first off, let's go over processes and threads. So first is going to be processes. So what are processes? I like to think of them as essentially just programs running on your computer. So you can think of your web browser. If you use Slack for work, that's running in a process. Also need Bash or Ruby scripts you run in your terminal. Those are all running in a process. Because if you think of your code as a list of instructions, the process is the thing that's actually executing those instructions. And so with each process comes a processor or a CPU core. And so each CPU core on your computer can run one process at a time. So if your computer has more than one CPU core, you can run more than one process at once. I think my computer has like 4, so I can run upwards of 4 processes at once. That doesn't mean, though, that there's only 4 processes on your computer. There are a ton of processes on your computer. I can even show you, if you have a computer handy right now, if you run the top command on Mac, I'm not sure it is on Linux or Windows, might be the same. If you run your top command on your Mac terminal, you can even see all the processes running your computer. I'll do it right now, too. Here's my terminal, and I'll see that. So if I run the top command, these are all the processes running on a computer. As you can see at the top left, these are the total processes, so there's much more than 4. Currently, I have 3 or 4 running, and most of them are sleeping. So you can see here, on the state side, is where you can see the actual running and sleeping states of your processes. And so you can see top right now is running because it's aggregating data for all processes. And Zoom probably is also going to be running every once in a while. Yeah, it's right here. Zoom is also running because I'm actually using Zoom computer. But for any process that's not being used, it's going to be in a sleeping state because I'm not actually using it. You can see, I don't have it right now, but if you had Google Chrome open, Google Chrome is a very memory-intensive application. You're gonna probably see like a list of processes on Google Chrome. They're probably all gonna be sleeping because if you're not using your browser, they're just gonna be on the background. You're not using each process all at once. The computer is constantly switching between processes. And so the other thing I want to show you from this is going to be this column right here. Basically, number of threads, number of TH, is the number of threads that each process is running. So you see, each process has a number of threads it's running. You can even see in the top right, all my threads are here. So I have close to 2,000 threads running. That's quite a few. So that kind of segues me into the next portion, which is, what are threads? So I like to think of threads as basically a subunit of a process. So whenever you initiate a process, in this case, the Ruby process, but any kind of process, it's going to start off with a main thread. And that main thread can spin off multiple child threads. And so there are different components to a thread, but the main two that we're going to focus on right now are just the stack and the heap. So the stack, or the call stack, is a data structure that, in your program, you're going to define functions, you're going to call functions. So whenever your process comes across a function and makes a function call, it's going to append that function to the stack. And so the more functions that you execute in your program, the more functions in your stack. So have you ever heard of the term stack overflow? That's because the stack is a finite size. So if you throw a recursive loop in there calling a bunch of functions, it's going to overflow. So that's the inspiration behind the website Stack Overflow. And then the other data structure that we have is a heap. And so the heap is where we store the defined variables and functions in a program. Each program is going to have variables and functions, and our process and thread need to access them. So they're going to get stored in the heap. So you can see from this diagram that each thread that we spin up is going to have its own unique call stack, meaning that whenever an individual thread executes a function, it's going to get appended to their own call stack, but won't affect the stacks of every other thread in the process. However, each thread underneath a single process is going to share the data heap. So each thread has the same access to all our variables and functions that we defined in a program. So I'm going to talk about that later, but just keep that in mind, that each thread has the same access to all the variables and functions. So one might ask, why use multithreading? What's kind of the point of it? So like the analogy I like to use is, you can think of the process as like a boss or employer, and a thread as a worker. And if you have, each process starts off with one thread, so each boss starts off with one worker. And let's imagine that your boss has 100 different tasks they need to do. If they only use one worker, that worker is going to take a while to get through all those 100 tasks. Instead, if they employ 100 workers to do each one task, then they could delegate work out so you can get more work done in a short amount of time. So that's kind of the point of multithreading, is to do more work in a short amount of time. And so we can't really talk about multithreading without talking about concurrency and parallelism. So that's kind of the crux, or the whole driving point of multithreading. And so I'm going to define these terms for you. So the first term we're going to define is just parallelism. It's a little easier to define because it's just tasks completed in parallel. I put without pausing and switching. I'm not totally sure that's the correct definition, but you can just think for now, tasks that are completed in parallel. So if you have two different tasks, or you get in the diagram up there, we have 4 different tasks, all starting and ending at the same time, all doing work. They're all doing tasks at the same time in parallel. Contrast that with concurrency, which is tasks overlap, but don't necessarily run in parallel. So you can have one task doing 5 different tasks, or if we can have one thread doing 5 different tasks. So we can have that one thread jumping between tasks all at once. So technically 5 things are happening, but they're all being done by one thread, and it's not doing them all at once, it's jumping between, so it's context switching between all those tasks. So that's the difference between concurrency and parallelism. Parallelism, in parallel, concurrency, overlapping, but not necessarily in parallel. So the reason why I bring this up is there are quite a few languages that implement parallel multithreading. So there's a lot of languages like Java where you can have threads running in parallel. So if you execute multiple threads underneath a process, it'll take advantage of the multiple CPU cores you have in your computer to run those threads in process. So hopefully I haven't confused you too much, because I'm going to throw a curveball at you where Ruby doesn't have that. Ruby, the standard runtime of Ruby, so the MATS Ruby interpreter, the MRI, kind of the Ruby runtime that everyone uses, can't achieve parallelism. The reason for that is because of the global interpreter lock. The global interpreter lock is essentially just a bottleneck. And no matter how many CPU cores you have in your computer, the GIL will only allow one thread to run at once. So Ruby, the standard runtime of Ruby, MRI, can get concurrency. You can have one, you can jump between a bunch of threads in sequence, but you're not gonna have multiple threads running at the same time. So that's kind of the crux of Ruby. And because of that, there have been a lot of jokes about Ruby before. Today, when I mentioned to my coworkers I was giving a talk on multithreading in Ruby, this was his response. You mean the fake lies, not real multithreading? That was a response about multithreading in Ruby. So like people might say Ruby might not have real threads because they're not OS level threads, it's not parallel. But even with that in place, you can still get a lot of benefits from doing multithreading in Ruby. So hopefully I haven't confused it too much, and if I have, we're gonna start getting to some examples. So hopefully the examples make it a little more clear. So let's get to some examples. So the first example is gonna be also before this. I'm trying to learn Vim at the moment, so bear in mind with me if I'm a little slow. So the first program we have running, or first one I do, is a simple counter app. You guys see that? A little bit, okay. So you can say on line 8, we're just running loop 1 through 10, and on each loop, we're outputting the number to the console. And you can see on the first line, I'm making the loop sleep for a second before outputting the number. So it's a pretty simple little script. There's no multithreading here. Let's kind of see how it works. Just trying to control how this works. Oh, wait. Something's happening with my. All right, 1 second. Yeah. There we go. So it's kind of running how we expect it, looping 1 through 10, waiting a second to output the number to the console. And then you can see at the end, I have a little thing that tells how long it took the script to run. So you can see it took a little over 10 seconds to run, which kind of makes sense. So let's see if we can use some multithreading to make this a little faster. So in Ruby, it's pretty easy to spin up new threads because Ruby conveniently gives the thread class. So to create a new thread, all we need to do is just call the thread class, help.new. And because threads are meant to do work, we're going to pass each new thread instance a block to do work to do in the form of block. So I'm going to just wrap this in a block. So each thread is going to, as we loop through, we're going to do thread.new, and we're just going to pass it the output block. So each thread is now, we're delegating the work out to each thread. So let's see how this works. Let's see if this works a little better. Well, we can see that it ran really fast. It ran in less than 0.1 of a second, but we're missing something. We're missing the actual numbers that the script's supposed to do. And the reason for that is because when we initiate new threads, we're giving it new work, the thread's gonna go off in the background and do the work, but the process is gonna keep going. So on line 8, when we do the loop through every thread and we initiate a new thread to do work, we're not telling the process to stop and wait for the threads to finish. So because we're not telling it that, the process is gonna keep going. So once the process is done with this loop, it's gonna go at the end, and once it hits line 13, the process is done. The script is done, there's no more work to do. So if you go back to that analogy about employers and bosses, if the business goes if the business goes under, all the workers are laid off. So if the process dies, all the threads under that process die with it. And so what we're gonna have to do is we're gonna have to tell the process to wait for all the threads to finish working before we actually exit the script. So we can do that so in order to do that, we need to keep track of our thread instances. So what I'm gonna do is I'm gonna create a threads array. And then when we initiate each new thread, I'm going to push it into our threads array. Just shove it in there. So that way we're keeping track of all the thread instances that we have alive. And then further on, so after the loop is done, we want to tell the process to wait for our threads to finish. So the way we do that is we're going to loop through all of our threads, and we're going to call the join method on each thread. So the join is essentially just telling each thread to join up with the process when it's finished. And so once our process hits line 13, it's going to wait for each thread to finish before moving on to line 15. So this is how we fully create a working, so I can kind of go back to that. This is how we use the thread. So whenever you submit a new thread, you have to tell the process for the thread to join back up before we keep going. So now let's try this and see how it runs. All right, you can see it took a little over a second to run. So that's pretty good, much faster than 10 seconds. But you might have noticed something else a little weird. All of our numbers, actually this one's pretty good. We have 1, 2, 3, but after that, the numbers kind of go crazy. And so the reason for that is because threads are asynchronous. So when we spin up new threads, they're gonna go off and do whatever threads do. The process can't keep track of them. So threads are not gonna finish necessarily in the same order that they were started. Sometimes they do, like we saw 1, 2, 3 finish in the right order. But we can't always predict that. Like if we were to run this program again, we're gonna have different order every time. So we can't predict when threads are gonna finish. And that's an important thing to realize, because if you have a program that has a lot of tasks to do, but you need them done in a very specific order, multithreading might not be the best solution, because it's gonna be very, very complicated, if not impossible, to enforce an order when you do multithreading. So it's kind of something that's important to realize. So that's the first example. So I kind of showed you how to create new threads as you go through. Let's make something a little more complicated. So I have a little inventory script. It's not really a real inventory script, but let's pretend it's an inventory script. So we're going to loop through all of our things, and we're going to create new threads. So on line 10, I have a loop. We're doing it 1,000 times. And then each loop, we're going to create a new thread. And each thread is going to do work in the form of fetching a resource. And if that resource was successfully fetched, then we're going to increment a counter. So this is the difference between the last script and this script. Now we're actually adding more things. So we have a count right here. So a count on line 7. Line 7 is where it's initiated, but line 13 is when we actually increment it. So now we're adding a shared resource to our script, because now, you see, each thread is initiating a new thread, and each thread is going to try and increment the same variable. As I mentioned before, all the threads underneath one process have the same access to the data. So they're all going to have access to that same variable. So what we're going to have is essentially 1,000 threads all fighting over this variable. And so, I mentioned before that if the fetch resource returns true, we can see on line 1 it's always going to return true. So essentially, in this program, we should have, you see, I'm outputting the count. We should have 1,000 at the end. But remember, as I mentioned before, we're having 1,000 threads all trying to fight over this one resource. So don't say anything, but think about in your head what you think the count is going to be when I run this. Don't say anything right now, but just think about it. And let's see if you're right. So let's clear the screen. So we're going to run who had 1,000? One person. All right, so I kind of misled you a little bit. So anyone know, not the person who raised their hand, but anyone else, why do you think it became 1,000? What was the reason why it actually worked this time? Not totally accurate. So the reason why this works is because of the global interpreter lock, as I mentioned before. Because I'm using the standard runtime of Ruby. I'm using Ruby 2.4. And so the GIL only allows one thread to run at a time. So because only one thread is going to run at a time, only one thread is ever going to increment this count up at any given time. So we're not going to have multiple threads fighting over it. So I kind of lied a little bit. But for the sake of argument, let's pretend you're not using Ruby. I know it's a Ruby meetup. Let's kind of stretch your imagination a little bit. Let's pretend you're using Java. Maybe Java allows. You're getting ahead of yourself. So let's just say Java, or let's say you're going to use a different runtime of Ruby or a different implementation. So yeah, so someone said JRuby. So JRuby is a Ruby runtime written on the JVM, so written in Java. And because it's written in Java, it does allow for parallel multithreading. And so let's just make sure. Sometimes I get some errors. So yes, we are using JRuby. And so now, what do you think is going to happen when I run the script with JRuby? Don't say anything, but ignore the errors, it's Java stuff. All right, we have 719. Who guessed 719? Good, you shouldn't have. If we do it again, yeah, so like I said, because they're synchronous, the threads are unpredictable. So we're not going to be able to guess how many counts is each time. So as I mentioned before, threads are asynchronous, but this is a little different from asynchronousness. This is more the fact that we're running threads in parallel. And what we created is a race condition. So a race condition is when we have multiple threads fighting over the same piece of memory. So in this example, it's actually very similar to the inventory example. We have two threads, and they're both trying to increment this 17 variable, or 17 number, to get to the next number. So since we have two threads, ideally we should get to 19. But in order to increment a variable, we first have to read it from memory, we have to update it or increment it, we have to rewrite it to memory. So since we have two threads pulling the variable, or pulling the integer at nearly the same time, they're both going to pull it when it's still value 17. So when they increment it and rewrite it, they're both writing it as 18. They're essentially overwriting each other. So ideally what we would have is we would have one thread increment it first, and then have the next thread, and then have the next thread try and increment it after the first one did. So we actually essentially have threads wait in line to access the variable. And so we can force that behavior by using something called mutex. So mutex, I believe, stands for like mutual exclusion object, or mutually exclusive object, something along those lines. But if you're ever a kid in kindergarten and your teacher had a special stick that only the person who could hold the stick can talk at once, and everyone else had to wait in line for that stick. I don't know if everyone else had that, but that's how a mutex works. If you have multiple threads trying to access the same resource at the same time, and you have a mutex in place, they're going to have to first check to see if the mutex is in use. And if it is in use, you have to wait. And once the mutex has been released, then they can access the mutex and also access their resource. So by having a mutex surrounding vulnerable code or our race condition, we can force threads to wait in line to access that resource. So we're ensuring thread safety, making sure that our program does not have inaccurate or corrupted data. So in Ruby, it's actually pretty simple to also, just as it's simple to create threads, it's also simple to create a mutex. So the first thing we do in order to use a mutex, we have to create a mutex. So let's do it on 8, and we're just going to create a new mutex. And in Ruby, that's pretty easy as well. So you have a mutex class. We're just going to call mutex.get. And so what we need to do is we're going to surround our vulnerable code in that mutex. So in order to use a mutex, we're going to use the synchronize method. Just make sure that all of our threads are in synchrony, or I'm not sure what that word is, but make sure that all of our threads are synchronous. So we're going to use the synchronize method, and we're going to pass it a block. And the block is going to be the code that's vulnerable. So in this case, it's going to be the counting, because that's our shared resource. And then, so yeah, that's it. We're just going to surround our race condition resource in our mutex synchronized block, and fine. So let's save this and see how it works. Sorry, I have to erase that one more time. All right, count 1,000. So there. By using the mutex, we have now ensured the thread safety of our script. So now we are having each thread wait in line. Even though each thread is running in parallel, we're making sure that each thread is accessing the shared resource one at a time. So now that I've gone over multithreading and race conditions and how to prevent race conditions with mutexes, let's use something a little more advanced. So I forgot to mention, but I'm going to end this talk with an example kind of inspired from a project that I did recently at DigitalOcean. So back in November, we released our CDN product, so like CDN in front of our object storage. And I'm on the storage team at DigitalOcean, so I was part of that effort. And one of my tasks was to create the public API endpoints for our CDN product. So allowing users to enable new CDNs, flush the cache, delete CDNs, update them. Basically a simple CRUD API. But we had a couple of requirements. DigitalOcean has a decent sized user base. We want to make sure that whenever a user tries to use our APIs, it's low latency, so it returns fast. So we want to have a fast endpoint. Ideally under a second. Maybe the tail latency can go a little over a second, but on average, ideally under a second. And also, we want to make sure that the information is accurate. So we don't want to return inaccurate data to our users. They're relying on us for the data. So I have a little sample API here. I wrote it in Sinatra. So what this API does is, it's not exactly CDN, nothing like that, but what we're doing is, it's supposed to emulate a API that's come in front of a data store. So you can see in the slow response, I'm pulling repos from a data store, in this case, the file. I didn't want to make an actual data store, but it kind of emulates the same thing. So we're pulling data from this file. So I'm just pulling repo data from our file, and it contains the repo owner and the repo name. They're all there. Next speaker. So we're going to pull that from, on the line side, we're going to pull that from our data store. Then we're going to initiate, I have a GitHub client that's going to be used to fetch information from GitHub. So what we're going to do is we're going to loop through those repos on line 12. And each time, so with each loop, we're going to fetch the data from GitHub. And then we're going to create a data hash, or a hash object that contains owner, the repository, the description, stars, forks, watcher language. So we're just basically creating a hash object, and then we're going to append that to a result array. And this result array is what we're going to return to our user. So when I call this API, it's going to return to me an array of repo object data, and then the time it took to finish. Hope I haven't confused it too much. So let's start the server, and so this, like I said, this is the slow response. So I'm just looping one at a time. Or let's see how long this takes, and if this is going to meet the requirements of our API to go less than a second. So we're going to so we have our Sinatra server running. So let's create a new shell. We're going to do a curl against it. So we're going to do localhost 4567 slow response. And then just to make the JSON a little nicer, I'm just going to do JSON format. So let's see how long it takes to get the data back from our API. Oh, thank you. This is what pair programming is great. There you go. Oops, I did this. So you can see it's taking a little while. Time spent. So actually, 4 seconds is actually probably the best I've ever had with this. Usually around 10 seconds. So let's try it more times. Yeah, maybe it's an anomaly. Oh wow. So GitHub's doing pretty well today. Because we are depending on the GitHub API for our API, we do have an upper limit how fast our API can get fast API essentially. But here, so we have about 4.8 seconds. So that's not quite meeting our requirements. We want to go ideally less than a second. So let's see if we can go a little better. So actually, I have to go back to mine. So we have another endpoint called the fast response. So the fast response is where I actually input some of the code. So you can see everything's similar except for down here, we do have a mutex because this result array where we're appending all of our hash data is a shared resource. We want to make sure that it's going to be, we're not going to have create any erase conditions with that. And so with each loop of our repo, of our repos array, we're going to loop through it, create a new thread. Each thread has a task of fetching the data from GitHub, creating that repo hash, and then appending it to the results array. So as I mentioned before, the results array is our shared resource, so I'll make sure that we're thread safe. So we're going to use a mutex block to surround it. And then we're going to call threads each, so we're making sure that the process waits to get all the threads for the threads to finish. And then we're going to return the response and see how fast it is. So let's see how fast this is right here. So we can just change the slow response to fast response. Let's see how fast this is. 0.6. Quite a bit better than 4 seconds. Let's try it one more time. So the tail latency can be a little higher. So this is 1 second. So it's not the best. Let's try it one more time. Okay. So on average, maybe around like 0.8, 0.9, smidge under 1 second. But that meets the requirement of our API. So before I go though, so that's kind of like everything I've talked so far was about threading, mutexes, that kind of stuff. So I have kind of the same pattern going on. But for a bonus API before I end the talk, I'm going to show you some little tricks of multithreading to maybe make this a little faster. So we go back to our Sinatra. We have a faster response. So here, so you can use mutex to essentially make sure that your program is thread safe. But so mutexes are only usually needed if you have a shared resource. So if there's a way to design your program to where you don't actually use a shared resource, it's probably the best, because when you add a mutex, not only are you adding a little more complexity because you have the chance of a race condition, you are also adding a little more overhead, because with a mutex, each thread has to wait in line. So there's a little more overhead with checking the mutex and making sure it's there. So with this, I designed it a little differently so we don't actually have a shared resource. Before, what we were doing is we had each thread in charge of creating that hash object and appending it to a shared resource. Instead, we're going to have each thread just return that hash object. And so there's another method that we can use in Ruby. So before I was using the join method on each thread, which tells it to join up with the process and wait. There's another method called value on line 101 right here. So we're gonna, if we call the value method on a thread when it finishes, not only is it telling the program to wait for the thread to finish, it's also going to return the return value of the thread. So right here, when we loop through each thread on line 82, I'm doing a map call on each repo. So so the result right here is going to be an array of thread instances, because each thread is going to return an instance of itself. And so we're going to end up with an array of thread instances. And then in the response, we're going to map through our array of thread instances and return an array of the return values of the threads. I hope that's not too confusing. But yeah, so we're essentially being a little more functional here. So instead of using like a shared state, we're a little more functional where we're actually using the return value of our functions. So let's see how this is a little faster. But also, in this directory, I'm still using the MRI. So let's see, for fun's sake, let's see how much faster it would be if I used you. So we have two things going on. We're getting rid of mutex, and we're also enabling parallelism. Actually, no, I have to end the server first. So we're going to be running our server in J. So let's see if we can get it even better. So I think before was like 0.6, maybe on average 0.9. So let's see if we can do a little better here. So if we just do faster. Oh, actually, it wasn't that fast, but we'll do a couple more times. 0.6. Okay. So I guess today it's not being a little faster. Sometimes I can get down to 0.3. 0.65. Okay, so today it wasn't acting up. It wasn't going with me, but it's still 0.6 on average, maybe 0.8. It still kind of meets our requirements of less. So yeah, that's kind of everything I have for you. I just want to end off with that example of actually using all the things coming over. But yeah, so thank you very much for listening to me, and
Okay, so does anyone have any questions? Come on, that was a great talk. No one has any questions. Oh, here we go.
So I guess like specifically for something like web development, say, and using Ruby, would there be a good case for multi-threading in a given situation? Because at least the way I go about doing web development, there is like a specific order to go about doing things, but would there be like a situation in which multi-threading would be efficient?
yeah, so when I mentioned the CDN API, so a lot of times if you're using a lot of third parties, that'd be good for using. So if you don't care so much about, so if you have multiple third parties that you need to retrieve data from, and you don't care what the order you retrieve them in, that's one example. So with the CDN, we use a third party to actually use kind of the CDN stuff, and their API is pretty terrible in the fact that it takes like 3 calls to actually enable a CDN. And so by kind of having each like delegating that work out, we make it a little faster by having multi-threading. And also when we retrieve, so our third party kind of had a lot of data, but we also had more data on our side. So what we would do is we would retrieve the data from their end, so the CDN end, and then we would loop through the array essentially of CDN data, and we would pull from our own database and append new data to it. So we added more metadata. So that's another case where if you're looping through a resource, instead of like, because each call requires there's gonna be some overhead doing like a serial amount of calls to a data store. So if you add some multi-threading to it and made it a little faster, it allowed us to get our Git requests, like the Git part of the REST or API, to be pretty fast. So it's in those cases. So yeah, you're not going to always find in web development. It's probably pretty rare to constantly use multi-threading every day, but there probably will be specific instances where you can use it to speed up your code.
Yeah, awesome. Thank you.
Exactly. Yeah. If you have IO, so whenever you do an IO, like IO instance, or like if your thread is going to fetch data from somewhere and it has to wait for that data to run, it's going to then spin up a new thread, because essentially in that point your thread is blocked. So your the scheduler on your computer, like your OS scheduler, is going to check to see if the threads are blocked, and when they are, they're going to swap out a new thread to run. So it makes it a little more efficient.
In the second example, I guess the last example where you were mapping it over, when you call at value to pull the value at, does it maintain the order in which the threads were mapped into the array, or does it do it first come first serve?
Yeah, so in that case, the order will be different. So probably if I ran this multiple times, so in this example, we have this repo as the last one. I'm sure if we went back up, it'd be a different one. So in this case, the order is gonna be a little different. So if this is a real production API, you probably want to maintain the order, maybe sort it a little bit. In that case, you could probably sort it. You could sort it afterwards, so you're adding a little more overhead with sorting, but maybe you can, so the fact that you use multi-threading can maybe make up for that fact. Yeah, not sure, there's quite a bit. Oh, so I mean, this one, it still ended with MyFlix, but I think I've run this a couple times, and yeah, sometimes there is a different order to it, but it'll return. Actually, no, actually you're right, because we're mapping over our threads and and we do the repos map, it's going to have the order of our threads, and then when we map over it again, we're pulling the return value each thread in each order. So it actually should maintain the same order. So actually, I guess I made it better than I thought it did. So the seeding API that I mentioned before, we actually wrote that in Go, because at DigitalOcean we use a lot of Go. Your question was, are they going to add that in Ruby 3? Oh. I actually don't know. There's one thing I like a lot about Go multi-threading is you have the channels between threads, so you can essentially allow threads to communicate across the channels. That's a really good model. I like that a lot. So if that's like one of the biggest things I know that's different between Go and Ruby. So if they were to adopt that from Go, that'd be a really big change. Yeah, but I don't know actually. I don't know if they're gonna make that.
So this is not really a question, but more of a follow-up to one of the questions. And the question was like, is multi-threading ever applicable to like normal Rails development? And one of the things to think about, I think, is that if you're using the latest Rails, then you're using multi-threading like every day, because the web server that comes with it is Puma, which spawns multiple threads. And you actually probably should know and understand that that's happening, because you could run into, even though there's a jail, you could run into, concurrency. I always confuse the concurrency and parallelism, but you could run into concurrency issues, and you are taking advantage of the fact that, while you're reading from the database, which is honestly what you're mostly doing anyway, that you're going to be yielding to other threads and you're going to be getting performance benefit. And the same thing goes for, I'm sure many of you use Sidekick. Sidekick has that same multi-threading model. It's been around for a while, and you're taking advantage of the fact that you're reading from the database mostly, and while you're reading from the database, your other jobs can run.
Yeah, it's actually a good point. I think because in web development, it's so high level that if you work in a lot of low level systems, there's gonna be a lot of chances we're gonna do multi-threading, especially with like Apache. I know Apache will maintain a pool of threads. So like threads are really useful in servers, because whenever you have a response come in, you wanna like dispatch new threads to take care of those responses. It makes your server much more available. Because if you only had one thread and you had one request to come in and another request right afterwards, you don't have to wait for that first request to finish. You want to spawn off new threads. So that makes, so I think a lot of times in web development, we've had a lot of that multi-threading and concurrency abstracted out because we're so high level, but there's a lot of it happening under the hood.
Thanks. Hi, I think earlier on when you were checking your Ruby version, I heard you mention guilds, is that right?
Yeah, like global interpreter lock.
I see, because when you mentioned that, I'd heard about, it reminded me of this concept of guilds. It's kind of being put into, they're talking about putting it into Ruby 3 to try to tackle a lot of the threading problems that Ruby has. I was just wondering if you, I guess now, if we're talking about the same thing or not, but if you had heard about it, if you can kind of touch on
No,
it.
I don't know a ton about Ruby 3.
Gotcha.
Yeah, I don't know a ton of what they're adding to it. But I mean, that the GIL is a common complaint. But at the same time, as I showed before, it made our inventory app, or made our inventory script run just kind of work out the box. So while you don't get the same like speed benefits, you kind of eliminate a lot of race conditions out of the box. So I mean, it's really good for not hanging yourself. Like Ruby, the standard Ruby version is great for that. If you get really in the deep in the woods and you need to really have more configurability, then maybe a different runtime or maybe Ruby is not the best option for you. But having the GIL there, there's some cons, but there's also a lot of pros to it.
Yeah, I actually have a question. How do you handle exceptions being thrown inside your threads before they fully return? And how do you deal with the zombie threads?
What was the second question?
How do you deal with zombie threads? Like they don't really tell the process that they fully like terminated.
That's a good question. So to be honest, I've used mostly multi-threading in Go. I learned a lot of multi-threading for this talk, but so in terms of exemptions, probably somebody here can probably answer that a little better, but I'm assuming if your thread runs into an error, it's going to return early, and maybe. And in terms of zombie threads, I don't actually, for that one, I actually don't know a lot about zombie threads in terms of Ruby. If anyone here has the answer to that, I would love to learn from it, learn it too. I guess crickets.
For next month. Do you have, okay.
All right, well, I think that's it. Thank you, everybody.
Thank you.
You guys can talk. Like, it's okay.